For more than 2 decades, scientists and cosmologists have been chasing a cosmic mystery. Where is half of the ordinary matter in the universe? Not dark matter, not dark energy, but the regular, baryonic matter, the protons, neutrons, and electrons that make up everything we can see and touch. According to precise calculations from the cosmic microwave background, Big Bang nucleosynthesis, and early universe models, this ordinary matter should account for around 4.9% of the universe's total energy density. But here's the twist. When we added up all the galaxies, stars, dust, and gas observable with telescopes, only about half of that expected matter was accounted for. The rest, missing. This enigma became known as the missing baryon problem. It wasn't just an oversight, it was a foundational issue in cosmology that cast doubt on our understanding of the large-scale structure of the universe. Let's clarify. Scientists weren't looking for exotic dark matter or mysterious forms of energy. They were looking for regular atoms, the kind you and I are made of. Simulations of the early universe, based on the physics of the Big Bang, told us we should be able to see this matter. So where did it go? The leading theory suggested that this missing matter wasn't really gone, it was simply hiding. It was believed to exist in an extremely diffuse form known as the warm, hot intergalactic medium, a spiderweb of superheated gas stretching between galaxies and vast, thin filaments that make up the cosmic web. But detecting this gas has proven almost impossible until now. A major breakthrough came from a team of astronomers using X-ray observatories, namely ESA's XM Newton and Japan's Suzaku. These instruments are capable of detecting high-energy X-rays emitted by extremely hot gas temperatures, exceeding 10 million degrees Celsius, precisely what we would expect from the GOIM. In this case, they focused on a structure in the Shapley supercluster, one of the most massive structures in our nearby universe. What they found was stunning. A 23 million light-year-long filament of hot gas connecting for large galaxy clusters. This colossal thread contained about 10 times the mass of the Milky Way, and most of it was made of ordinary baryonic matter. The temperature, density, and spread of the gas perfectly matched theoretical predictions that had been made by cosmological simulations decades earlier. As astrophysicist Konstantinos Makais said, the models were right all along, while X-ray telescopes were providing direct visual confirmation. Another method was also closing in on the missing matter, this time using fast radio bursts. FRBs are brief, powerful pulses of radio waves that originate from distant galaxies. When these signals travel through space, they pass through different kinds of matter, which causes the signal to slow down and disperse at different frequencies. By carefully measuring how these bursts spread out over time, scientists can estimate how much matter they pass through, essentially mapping the intergalactic medium. A recent study compiled data from dozens of FRBs and found that roughly 76% of the universe's ordinary matter lies in the intergalactic medium, with the rest in galaxy halos 15% and within galaxies 9%. This lines up perfectly with what simulations and X-ray observations suggest. So now we have 2 independent lines of evidence: X-ray imaging and FRB dispersion, both pointing to the same solution. The missing matter was never missing, just hidden in plain sight within the whim of the cosmic web. Solving the missing baryon problem isn't just about checking off a cosmic to-do list. It has deep implications. Model confirmation. This discovery confirms the lambda-called dark matter LCDM model, which has been the dominant framework in cosmology. It tells us that our simulations of the early universe and its evolution were on the right track. Better understanding of matter distribution, knowing where baryonic matter resides, helps scientists model galaxy formation, gravitational interactions, and even star production. Improved cosmological measurements accounting for all matter allows for more accurate calculations of the universe's total mass energy content, aiding in our understanding of expansion rates in cosmic history. A new window for observation. Now that we know where to look and what signatures to seek, astronomers can more confidently explore the WHIM in other regions of the sky, building a more complete map of the universe. This discovery opens the door to a new era of observation. As new telescopes like the Athena X-ray Observatory set to launch later this decade and come online, we'll be able to map these cosmic filaments in even greater detail. Additionally, with more fast radio burst detections coming from observatories like Chi, eventually, we may be able to trace the complete flow of baryonic matter from the early universe to today, revealing how galaxies like our own formed and evolved in the cosmic web.